Electricity is amazing. It powers our homes, our phones, and even our bodies. But what exactly is electricity? How does it work? These are important questions. To understand electricity, we need to learn about Ohm's law. Ohm's law is a fundamental principle that describes how electricity behaves in a circuit. Don't worry, it's not as complicated as it sounds. In this essay, we're going to break down Ohm's law into bite-sized pieces, using simple language and real-world examples. By the end, you'll be able to impress your friends with your newfound electrical knowledge. Before we dive into Ohm's law itself, let's meet the three main players: voltage, current, and resistance. These three elements are fundamental to understanding how electrical circuits function and interact. They are the building blocks of any electrical system, and without them, we wouldn't be able to harness the power of electricity in our daily lives. Whether you're charging your phone, turning on a light, or running a complex machine, voltage, current, and resistance are at work behind the scenes. These guys are always hanging out in electrical circuits, and understanding their roles is key to unlocking the secrets of electricity. Imagine them as a team working together to make sure everything runs smoothly. Voltage provides the push, current carries the charge, and resistance controls the flow. Each one has a unique role, but they all depend on each other to keep the circuit functioning properly. Voltage, V. Think of voltage as the electrical pressure that pushes electrons through a circuit. The higher the voltage, the stronger the push. We measure voltage in volts, V. Voltage can be generated in various ways, such as through batteries, which convert chemical energy into electrical energy, or through generators, which convert mechanical energy into electrical energy. This push is essential for getting the electrons moving and creating a flow of electric current. Current, I. Current is the flow of electric charge, like a river of tiny particles moving through a wire. The more electrons flowing per second, the higher the current. We measure current in amperes or amps, A. Current can be direct, DC, where the flow of electrons is in a single direction, or alternating, AC, where the flow of electrons periodically reverses direction. Understanding the type of current is crucial for designing and working with electrical systems. Resistance, R. Resistance is like friction for electrons. It's the opposition to the flow of current. Materials with high resistance make it harder for electrons to flow, while materials with low resistance let them zip through easily. We measure resistance in ohms, omega. Different materials have different levels of resistance. For example, metals like copper have low resistance and are excellent conductors, while materials like rubber have high resistance and are used as insulators. Understanding resistance is key to controlling the flow of current and ensuring the safety and efficiency of electrical systems. Now that we've met the main characters, let's see how they interact. Ohm's law describes the relationship between voltage, current, and resistance with a simple equation, V equals Y times R. This equation tells us that voltage is equal to current multiplied by resistance. In other words, the amount of electrical pressure needed to push a certain amount of current through a circuit depends on the resistance of that circuit. Sometimes abstract concepts like electricity are easier to grasp with a helpful analogy. One of the most common analogies used to explain electricity is comparing it to water flowing through a hose. This simple comparison can make understanding voltage, current, and resistance much more intuitive. Imagine a garden hose connected to a faucet. When you turn on the faucet, water starts to flow through the hose. The faucet controls how much water comes out, similar to how a power source controls the flow of electricity in a circuit. Voltage is like the water pressure from the faucet. When you turn the faucet handle to increase the water pressure, more water is pushed through the hose with greater force. In an electrical circuit, voltage is the force that pushes electric charges through the wires. Higher pressure means more force pushing the water through the hose. Similarly, higher voltage means more force pushing the electric charges through the circuit. This increased force can make devices work more efficiently or power more demanding equipment. Current is like the flow rate of the water, how much water is flowing through the hose per second. In an electrical circuit, current is the rate at which electric charges flow through the wires. Just as a higher flow rate means more water is moving through the hose, a higher current means more electric charges are moving through the circuit. Resistance is like the width of the hose. A narrow hose restricts the water flow, making it harder for water to pass through. In contrast, a wider hose allows more water to flow through easily. In an electrical circuit, resistance is the opposition to the flow of electric charges. A narrow hose restricts the water flow, while a wider hose allows more water to pass through easily. Similarly, higher resistance in a circuit makes it harder for electric charges to flow, while lower resistance allows them to flow more freely. Just like with the hose, higher voltage will push more current through a circuit, but higher resistance will make it harder for the current to flow. Understanding these basic principles can help you grasp more complex electrical concepts and how they apply to real-world situations. So next time you see a garden hose, remember the analogy and how it relates to electricity. Section 5, Formula Fun Solving for the Unknowns. Ohm's law is like a magical formula that can help us solve for any of the three variables if we know the other two. Let's rearrange the equation to see how. To find current, or I, it's I equals V divided by R, that's voltage divided by resistance. To find resistance, or R, it's R equals V divided by I, that's voltage divided by current. With these simple rearrangements, we can calculate the missing value in any electrical circuit. Section 6. Real-world applications, Ohm's Law in action. Today we delve into the fascinating world of Ohm's Law and its practical applications in our everyday lives. From the devices we use to the safety measures in our homes, Ohm's Law is at the heart of it all. Ohm's Law isn't just a theoretical concept, it's used every day in countless practical applications. Whether it's in the design of complex electronic circuits, or the simple act of charging your smartphone, Ohm's Law ensures that everything functions smoothly and safely. Circuit design. Electrical engineers use Ohm's Law to design circuits for everything from smartphones to airplanes, ensuring that components receive the correct voltage and current. This meticulous process involves calculating the resistance, voltage, and current to create efficient and reliable electronic devices. Without Ohm's Law, the precision required in modern electronics would be impossible to achieve. Appliance safety fuses and circuit breakers in our homes rely on Ohm's Law to protect us from electrical overloads. These safety devices are designed to interrupt the flow of electricity if the current exceeds safe levels, preventing potential hazards such as electrical fires and damage to appliances. If the current gets too high, these safety devices break the circuit, preventing damage and fires. This automatic response is crucial in maintaining the safety and integrity of our electrical systems. By understanding and applying Ohm's Law, electricians can ensure that our homes and workplaces remain safe environments. Medical equipment. Medical devices like EKGs and pacemakers use Ohm's Law to measure electrical signals in the body, helping doctors diagnose and treat patients. These devices monitor the electrical activity of the heart, providing critical information that can save lives. By applying Ohm's Law, medical professionals can ensure the accuracy and reliability of these life-saving tools. From the moment you plug in your phone to charge, to the sophisticated medical equipment in hospitals, Ohm's Law is at work. It governs the flow of electricity, ensuring that devices operate safely and efficiently. Understanding this fundamental principle allows us to harness the power of electricity in innovative and life-enhancing ways. Section 7. Power up, the energy connection. Ohm's Law is also closely related to power, which is the rate at which electrical energy is used or transferred in a circuit. The formula for power, P, is P equals V times 1, voltage multiplied by current. Using Ohm's Law, we can express power in terms of resistance as well. P equals I squared times R, current squared multiplied by resistance. P equals V squared divided by R, voltage squared divided by resistance. Understanding power is important for choosing the right components for a circuit and for calculating energy consumption. Section 8. Series and parallel circuits. Different paths, different rules. Electrical circuits can be connected in series or parallel, and Ohm's Law applies differently in each case. Series circuits. In a series circuit, components are connected one after another like a single loop. The total resistance is the sum of individual resistances. Parallel circuits. In a parallel circuit, components are connected on separate branches, providing multiple paths for current to flow. The total resistance is calculated differently, and each branch experiences the same voltage. Understanding these differences is crucial for analyzing and designing more complex circuits. Section 9. Conclusion. Ohm's Law, your guide to the electrical world. Congratulations, you've now explored the fascinating world of Ohm's Law. You've learned about voltage, current, resistance, and how they're all connected. You've seen how this simple yet powerful law governs the behavior of electricity in everything from tiny circuits to massive power grids. So next time you turn on a light, charge your phone, or marvel at a lightning storm, remember Ohm's Law, your guide to understanding the wonders of electricity.